Namaskar and welcome back to this module of lectures on concrete engineering and technology. We are trying to revise fundamentals of concrete, proportioning of mixes, stages in concrete construction, issues in quality control, talk about special concretes, some mechanisms of deterioration, reinforcement in concrete structures, and maintenance of concrete structures. In the last discussion, we were talking about a subject which spans fundamentals of concrete design, in fact the principles of all structural design as a matter of fact, mechanisms of deterioration in concrete, and maintenance of structures. What we were talking about was a conceptual framework for maintenance and repair of concrete structures. So to recapitulate what we were trying to do, we had studied or looked at deterioration and performance and how they change over time. So this here is the variation of deterioration. As gradually the structure is in service for a longer and longer time, it deteriorates. Corresponding to that deterioration, the line here shows a change in the performance. Initially the structure performs very well, and as the structure ages, the performance tends to reduce or degrade. Taking these changes in mind, this green line here is the minimum acceptable level of performance, and this red line here is the maximum acceptable level of deterioration. And depending on how we want to define the concept of service life, we can say that the service life is reached once either the deterioration exceeds the maximum permissible limit or the performance falls below a critical minimum acceptable level. Now, how do we define these levels? In what quantitative parameters? That is left to us. We could choose parameters such as deflection for performance. We could choose cracking for deterioration, chloride penetration for deterioration, and so on and so forth. So as a concept, this is what we had talked about when we talked about in-service maintenance of concrete structures. Extending this concept further, we discussed the issue of inspection, which involves determination of the actual state of the structure from the point of view of either deterioration or performance. So once the structure is put in service or just before it is put in service, there is an initial inspection followed by periodic inspections, and at the end of which we need to carry out an evaluation process and decide what we want to do, either reinforce the structure or at the end of any stage we can decide to repair the structure. This could be followed by a detailed inspection, which again could lead to a repair or a reinforcement. And at the end of this cycle, once we have carried out a repair or a rehabilitation, we really go back to an initial inspection and see whether the work that has been carried out is satisfactory and what is the step or what is the state from which the structure is starting afresh. While we are talking about this, we also talked about the need to understand deterioration and its causes when we are carrying out inspections, and the importance of selecting repair and reinforcement measures when we are carrying out repair and reinforcement. And of course, the issue of evaluation, which is really a judgment or a decision making process which is involved at different stages to help us determine the next step. Now, carrying this forward, we try to define the concept of repair in terms of a maintenance action which may not increase or improve the existing state of the structure, but increases the service life that is available to us by reducing the rate of deterioration that is occurring at that point in time. So, if we are intervening at this point in the structure, we have increased the service life by reducing the rate of deterioration or rate of further deterioration. Similarly, as far as reinforcement is concerned, if we are intervening at this point in time, we may actually improve the performance at that point in time, and how this graph, that is the post reinforcement change in the performance, goes would depend on the nature and the efficiency of the reinforcement work. So, we have increased the service life from this point to this point because of reinforcement action. So, this is what we had talked about last time. We had discussed in some detail the causes for repair and reinforcement action, considering a simply supported beam like this. One of them could be increase in the load level, which in civil engineering structures could arise out of changes in the axial load, the frequency of loads and so on. It could be in the decrease of the load carrying capacity of the member or the structure, which is how the deterioration in properties of the material manifests itself. And there could be changes in the acceptable response or the change in the design criteria, acceptable deflections, for example, changes in the load factors and so on. We had talked about some problems in repair. We had talked about a bad repair, in which case we had seen that the repair material, for example, polymer cement mortar, is placed in a structure like this without removing all the concrete from behind the deteriorated reinforcement bar, which is what is done here as a good replacement. And a replacement of this nature or a repair action of this nature does not necessarily mean that the structure will not corrode in the future. So, the corrosion or such a problem could manifest itself very quickly after the repair work has been carried out if the work is not done properly. We had talked about the need to evaluate repair material and the method. It is not necessary that expensive materials are always more durable. We had talked about periodic repair of coatings, because those coatings could be deteriorated or could lose their effectiveness on account of deterioration by exposure to ultraviolet rays. In cases of corrosion, we have to be careful about macrocell corrosion being initiated, and we have talked about macrocell corrosion when we were talking about deterioration in concrete structures on account of reinforcement corrosion, and the need for education and training of professionals for inspection and evaluation of concrete structures, which is a professional job. It just cannot be done on an ad hoc manner. So, now coming to what we will talk about today, we will really focus on some of the common methods of repair and reinforcement, and we will quickly run through some results from a laboratory study on repair methods and their efficiency. Now, coming to some of the common methods of repair and rehabilitation, the discussion here is more in terms of introducing the repair methods rather than going into the details of each of these methods. And I would like the listeners and the students who are interested in this subject to actually go through the net and some of the available literature which describes each of these processes in much greater detail, and that perhaps is not required when we are talking about the general principles of repair and reinforcement of concrete structures, that too within a framework of operational maintenance and so on. Now, coming to the first such method that we talk about is the dry pack and epoxy bonded dry pack. Now, what is done here is that we have a situation here or a portion of the structure here which needs to be repaired. So, what we put in place is a restraining formwork, and we try to pack the repair material in layers. So, we put this layer first, followed by another layer after that, and so on, and this compaction is carried out using a hammer. So, that is the manual method for placing, compacting and ensuring that this part of concrete which had been removed or which had to be removed on account of some reason is now replaced by another material. Now, this material could consist of a cement sand mix, which is basically cement mortar with just enough mortar. So, it is basically a very dry mix, because the compaction that we are doing is with a hammer, and that we can obviously do only if the mix is dry. And as we said, the repair material is placed in thin layers and compacted with a hammer. Instead of a cement based binder, we could also use a epoxy based binder, in which case what we would call this method is epoxy bonded dry pack, and the method is obviously suitable only for small areas and susceptible to changes in the quality of the work done depending on the workman involved, because all the operations are strictly manual. The mixing, perhaps, the compaction is completely manual, and so on. Coming to the next method, we have pre-placed aggregate concrete. Now, this is another method where a formwork first, as shown here, pack this space with gap graded coarse aggregates, compact the aggregates, and finally inject cement grout through pipes or tubes which are going right to the bottom, and gradually withdraw the pipes as the grout rises in the pre-placed aggregate. The advantage of this method compared to using simply concrete to begin with would be that we do not really need to compact the concrete. It can be done in sections where concrete cannot be placed and compacted. So, we can use coarse aggregate, fill that space with coarse aggregate, and add the grout later on. There are basic differences between pre-placed aggregate concrete and normal concrete. The way pre-placed aggregate concrete has been done, as you know, would involve aggregate to aggregate contact, which is not necessarily true when we are talking about normal concrete constructions. Similarly, the gradation of the aggregates that is used should be such that it facilitates or allows the movement of cement grouts. We need to engineer the properties or determine the properties of the grout that will be suitable for a particular application depending upon the maximum particle size and the particle size distribution, which would essentially control the void geometry of the compacted coarse aggregates. So, grout is forced into voids of clean graded coarse aggregate densely pre-packed in formwork. It consists of cement, sand, pozzolana and superplasticizers. Coarse aggregate should be washed to remove all fines and deleterious materials, and grouting begins at the bottom of pre-placed aggregate. Obviously, we cannot start the placing of grout at the top and hope that the grout will simply flow down. It is better to start from the bottom and then go up gradually. These are some more pictures from pre-placed aggregate concreting operations. The first step is to fix the formwork and gap graded aggregate washed, free of fines, bond inhibiting materials placed in the cavity. We could use reinforcement here if we want, followed by forms are fitted with pipes and nipples and valves for placement of the grout. So, all these paraphernalia is added to this system. We can close this system completely, which we cannot do when we are trying to place concrete in the cavity like this. Step 3 would be flowable grout is mixed and pumped into the cavity formed, filling space between the aggregate. So, of course, we have to have a vent through which the air is allowed to escape, and finally, the forms are removed and the surface is finished. So much for the pre-placed aggregate concrete operation. You can imagine that an actual placement of pre-placed aggregate concrete would be a lot more complicated, and the quality control even more so, because we need to understand the void geometry, we need to understand the void configuration for a given mix of aggregates, and we need to choose an appropriate grout from the point of view of the viscosity, the segregation, bleeding, strength, and so on. Continuing our discussion with methods of repair, shotcrete is another candidate, and we have talked about it earlier when we were talking about special concrete. There could be wet concrete mixes or wet mixed shotcrete and dry mixed shotcrete. In the dry mixed shotcrete, the water is added just before the material is shotcreted onto the surface, and the method is called also goniting or pneumatically applied concrete or mortar, as it involves deposition of material in layers under pressure without supporting formwork. And this part limits its applications. Of course, as a repair method, it is a very powerful method because material can be deposited in layers. It can be done by the dry or the wet mix process, and the method is particularly useful for restoring spalled surfaces. If we have a surface where the concrete has really fallen off, then shotcreting or goniting or placing concrete under pressure is a very viable alternative. This is quite different from having to place the concrete manually in that area. Now, let us talk about another method which is quite different, and that is plate bonding. Now, this consists of connecting mild steel plates to concrete surfaces mechanically by bolting or gluing with epoxy. As we can see here in this picture, fixing of plates on the concrete surface would enhance the flexural strength, and the plates can be held in position by either bolting them to the concrete or fixing them using an epoxy. So, what primarily is being done is that we have what we have in this method is that if we have a concrete beam which has deteriorated, what we want to fix is a mild steel plate here, and then if we apply load on this beam, this plate takes all the tension. So, this increases the load carrying capacity of the repaired beam. Now, what has to be ensured in this process is that this plate is properly held in position either by gluing at the concrete surface or by appropriately anchoring the plate into the existing concrete, and that is what is meant by saying bolting or gluing with epoxy. And we have a steel plate which has been placed here for the tensile face. We can place these plates even on the shear faces and so on. This is an inexpensive, versatile and advanced technique for rehabilitation, except that we should know how to design this method. We should know what is the kind of plate to be used, what is the size of the plate, what is the size of the bolts, or what is the kind of epoxy or glue which has to be used at the surface in order to ensure monolithic structural action, but it can substantially increase strength, stiffness and ductility of the repaired structure. We could even use L plates if we want to use in a beam or a column. Now, let us talk about jacketing. Jacketing really means an existing concrete around which fresh concrete is placed. So, that is a concrete jacket, we call it RCC jacket, means a reinforced cement concrete jacket is placed around a concrete which could have deteriorated, in which case it could be a repair action without an intention to increase the load carrying capacity or the performance of that column or that structural member, or it could even be a reinforcement step where we want to actually increase the cross section of that particular structural member. So, what is being done is that we add stirrups which are welded, we add longitudinal reinforcement, and this longitudinal reinforcement is anchored in the existing concrete somehow with a resin mix, and we finally concrete the outside surface. And this can be done either by normal concreting, that is placing the formwork and pouring the concrete, compacting it and so on, or it could be done by shotcreting, or it could be done by pre-placed aggregate concrete. The idea being that there is reinforcement outside an existing structure and a concrete covers that to increase the cross-sectional area or keeping the cross-sectional area the same and so on. When we are doing jacketing, we need to be especially careful about the need to provide shear key bars, and these shear key bars are bars like this, which are provided to ensure that the newly added material, that is the jacketed concrete, becomes monolithic with the existing concrete. Now let us talk about stitching. Suppose we have a crack like this in a structure. One of the options available to repair this crack or prevent this crack from spreading, either lengthening or increasing in width, would be to stitch it. Now how do we stitch it? We mark and drill holes on both sides of the crack, that is here and here across the crack, chase a groove between the drilled holes, so we make a chase or a groove around across this crack like this, insert a U-shaped MS bar in the holes that spans the crack and grout this on either side and fill the chase. So what has happened is that this crack now has these U-shaped clips or MS bars which are spanning the crack. Now as the crack tries to move, it has to cause failure of these clips before the crack can move. So effectively these MS rods or clips serve to arrest any crack growth, because the steel is not so easy to fail. It is not so easy to apply enough stress on the steel to fail. Steel is a fairly high strength material. As far as filling of these grooves is concerned, we could do it with mortar, we could do it with concrete, we could do it with epoxy concrete, whatever we want. Now let us talk about a fiber wrap. Now fiber wrap is basically another form of jacketing, where the deteriorated concrete here is wrapped with fiber. So it is a non-intrusive strengthening to increase the load carrying capacity with minimum damage to existing concrete. Several layers of bidirectional woven material or woven fabric is held together with an appropriate resin. So it is not a single material here, or it is not a single layer of fiber, it is several layers of bidirectional fibers woven and held together with an appropriate resin. And in a manner of speaking, as I said, it is just another form of jacketing. So instead of a reinforced concrete jacket, we are placing a FRP jacket on a deteriorated concrete member. It is very effective as far as columns is concerned, but it can also be used for other members. You will recall that we had some discussion on use of FRP materials for repair and re-strengthening of concrete members or deteriorated concrete members when we were talking about the applications of fiber reinforced plastics in civil engineering construction. And now coming to perhaps the last basic method for repair of concrete structures that we are talking about today, we come to external stressing. Now what is external stressing? We must remember that cracks in concrete can be closed by inducing a compressive force which is sufficient to overcome the tension which has caused the cracks. So basically, if we have a concrete member with cracks like this, if we apply a sufficient compression on the concrete as shown, the chances are that we will be able to close these cracks. And once we are able to close these cracks, half of our battle as far as reducing the rates of deterioration has been won, because these cracks are not only maladies from the structural point of view themselves, but also provide easy ingress to deleterious materials such as carbon dioxide and air, water, maybe chlorides into the concrete. and that accelerates the deterioration process. If we are able to close these cracks, we would at least be able to slow down the ingress of these materials into concrete. And how can we induce this kind of compression is what we get when we externally stress, or this is what is called external prestressing, out cable prestressing. Now, without getting into the details of this out cable prestressing, because we have talked about it earlier in this course, we will just recall pre-tensioned prestressing, where reinforcing tendons are tensioned in stage 1, concrete is cast and allowed to harden, and then the stress is transferred to concrete to induce compression. As contrast to post-tensioned prestressed systems, where concrete is cast normally, leaving ducts within, tendons are placed within these ducts and tensioned after curing of concrete, and once the tension is removed using appropriate anchors at the ends, the concrete is placed in compression. Externally tensioned prestressed, which is of interest to us now in these kind of externally tensioned prestressed systems, which are of interest from the point of view of repair and rehabilitation of structures, is a system where prestressing tendons are placed outside the concrete and there is no continuous bond. Once these tendons are outside, of course, they have the merit that any problems in terms of maintenance can be actually monitored at the points of anchorages, the points of supports, the tension in these tendons and so on. So, what we had said at the outset today, that we will focus on some of the common methods of repair and rehabilitation, and that is something which we have now completed, having gone through a variety of methods which are used or can be used in concrete structures apart from simple methods such as impregnation of cracks, application of coating, placing an overlay and so on. We have not gone into the details of these methods, we have not gone into the design of these methods, and that is something which is very, very important. One can imagine that each of these methods has structural implications. When we are talking about a fiber wrap, when we are talking of RC jacketing, when we are talking of MS plate bonding, they tend to alter the structural behavior of the members and therefore the structure. So, any such method, the use, what kind, what time, what nature and so on, must be decided by a structural engineer or in consultation with a structural engineer who should assess the implications of carrying out this maintenance action on the behavior of the structure. Now, having said all that, let us quickly run through some results from laboratory studies on repair methods and their efficiency, which will give you an idea as to what is the kind of work that needs to be carried out from an engineering point of view to better understand the different materials and their efficiency as far as repairing and reinforcement of concrete structures is concerned. What we will talk about is two studies. The first one is an experimental study to evaluate failure surface of the concrete repair material interface, and this study was published in Seisang Kenkyu, which is a journal of the Institute of Industrial Science, University of Tokyo some time ago. Now, if we look at a reinforced concrete beam with a repair as shown here, what we understand is that the behavior of this beam after it has been repaired would change depending upon factors such as the location of the repair, whether it is on the top face, that is the compression, the way it is shown, or the bottom face, which is the tension face, the location of the repair, whether it is in mid span or close to the supports, the depth of repair and so on. Apart from all that, it will obviously depend on how the old concrete and the repaired surface bonds, that is the interface of the old surface and the new surface. So, as a part of this study, the discussion really in this research work was focused on an understanding of the interface, and different combinations of stress of concrete can be expected depending on the extent and location of repair. In this portion here, we would expect a certain state of stress. If the repair was being carried out at this point, we would expect another kind of stress, and so on. So, we really need to understand how the interface behaves under the action of different stresses. So, compatibility of repair materials with the parent concrete in terms of material and mechanical properties for effective repair needs to be ensured. And of course, once we have the basic properties with us determined experimentally, we could use finite element methods or any such program to simulate or analytically examine the behavior of a repaired concrete beam. Now, as far as the steps in the specimen preparation is concerned, there is the base concrete which is cast and left to cure under gunny bags for 28 days. The surface is roughened using a water jet. Repair material is cast or shotcreted, with the composite specimen being left to further cure in air for another 4 to 7 weeks. And in this case, different tests were carried out. For the pure tension test, this here outlines the basic process: casting the concrete block of 500 by 500 by 80, on which a certain layer of 20 mm of repair material is to be placed. The surface preparation is carried out, repair material is overlaid, and a drill is used to create a specimen which is shown here, and then we carry out a pull-off test. A pull-off test really means fixing a fixture on the surface and trying to pull it off, trying to ensure thereby failure in this small neighborhood, whether the failure occurs within the repair material or at the interface or in the concrete. So, now in order to do that, this depth that we make as far as the coring is concerned is fairly important, and this here shows a failed specimen. As far as a direct shear test is concerned, a concrete prism is cast, the concrete from the middle is removed, and we carry out an appropriate exercise as far as the surface of the concrete is concerned, cast the repair material here, and then finally subject the specimen to shear. It should be remembered that this process of casting the concrete prism and then removing the concrete is not the same as casting this block of concrete and this block of concrete first and then placing this repair material within. The reason for that is that in case we cast the concrete and then just place the reinforcing material and then place the repair material within that block, we would not be doing any surface preparation of the concrete. The concrete at the surface would not be really the same as the concrete that we would get after removing the concrete which is originally cast. So, these are some fine differences or points that one must remember when we are doing an experimental work. We must try to simulate the actual or the field conditions to the extent that is possible. When it comes to a combined shear and compression test, a cylindrical specimen 75 millimeters in diameter and 150 mm long was prepared. The cylinders were cut at a slope of 30 degrees to the longitudinal. After whatever surface preparation had to be done, the cylinders were recast using the repair material. So, we cast the cylinder here, remove part of this cylinder, and then fill this part with the repair material and test this composite cylinder and see what happens at the interface as far as failure is concerned. These are some of the results which have been obtained from the pure tension, pure shear, compression and shear values for different surface preparations. The values are different, and of course, these are the results for the compressive strength, Young's modulus, Poisson's ratio and the tensile strengths of the individual concrete and the repair material. So, you can see that the compressive strength of the repair material per se is much higher than that of concrete, but the Young's modulus, the Poisson's ratio and the tensile strengths are not so much apart. Now, coming to another experimental work which was an extension from the previous one where we studied the interface. This one was behavior of repaired RC beams under cyclic loading, and this was also published in the Se-Sankenkyu. Here 8 beams were repaired and non-repaired control beams were there, and they were tested to and they were subjected to fatigue, that is repeated loading. We used 2 repair materials and the beams were repaired over a length of 80% of the span. The depth of repair was kept at 2 levels, the cover thickness plus about half the diameter of the bar, and in another case the repair thickness extended 20 millimeters beyond the reinforcing bars. Now, this is similar to the kind of discussion that we had earlier about a good repair and a bad repair system. In one case, if this is the bar, the repair material was cast up to this point, which is the cover depth plus half the diameter of the bar. In another case, the repair material extended all the way beyond to the extent of 20 millimeters behind the bars. And as we said, there were 2 repair materials used, one was cement based and the other was polymer based. This is a typical sketch or a diagram which shows the dimensions and the reinforcement details of the reinforced concrete beam used. The beams were all under reinforced with the main reinforcement of about 1.18%. The x by d, which is the neutral axis to the effective depth ratio, is about 0.24. Nominal shear reinforcement being used. These beams were finally tested for fatigue. The original concrete beams were cast using an appropriate thermocol piece at the location to be later covered with repair material. This thermocol piece was obviously removed, and then was obviously removed at the time of placing the repair material. The beams were cured for 4 weeks. The exposed concrete surface was roughened using a high pressure water jet, and primer was applied at the concrete surface to improve the bond between the parent concrete and the repair material, and that is typically done even when we are carrying out the repair and reinforcement work in a site. And the repair material was applied using shotcreting, whether it was cement based or it was polymer based. In this case, the repair was done using shotcrete. 4-point loading test was carried out using an A by D ratio of 5.1. The upper and lower limits of fatigue cycle test were set at 20 to 75% of the maximum static load, and the frequency of load without load reversal is 1.5 hertz. So, this really describes the fatigue test. So, we should remember that if we without getting into the details of how fatigue tests were carried out or how they should be carried out, let me just explain the principle of a fatigue test here. When we are testing a reinforced concrete beam in static loading, forget about fatigue loading. If it is static loading, what we do is keep increasing this load till the beam fails. Now, in a fatigue load or a repeated application of load, we increase the load to a certain level and then cycle it the way it is shown. Now, this level, which is the maximum load level, has been kept at 75% of a static load carrying capacity of the beam. If this load level here is allowed to come to 0, and in fact the load could be applied from the other side, and that is what is going to happen in a true reversible test of a reinforced concrete beam, where the beam is subjected to loading from both sides, and the top and the bottom lose their meaning, in the sense that when the load is applied from one side, a certain side is in compression and the other side being in tension, and if the load is being applied from the other side, the tension and compression phases change. In this case, instead of doing that, without load reversal, we continued the load to be only in a manner that this does not happen, and this phase continues to be in tension all the time, except that the extent of tension or the amount of tension changes as the load is being applied. So, now this load level was kept at 20% of the static load carrying capacity. So, with this 20% and 75% serving as the bounds of the load applied, this test was carried out, and the attempt was to determine the number of cycles to failure. The deflection, as we were performing these tests, was also measured using normal transducers, and this here gives us the cycles to failure as far as the different beams are concerned. So, instead of, this is in thousands, so if you add another 3 zeros here, 1.27 or 1.3 million cycles for the control beam, this shows the number of cycles at which the beams failed, and this gives us the percentage of the fatigue life of all these beams. Now, we will not get into the details of the discussion, but we must note that the values range from 18% or 18.5% to situations where the beam has actually become stronger than the control beam. One must remember that these are, after all, only single beams that have been tested, and that is something which I wanted to point out, to flag to you the importance of actually carrying out tests which are more in number, so that we are more confident about the repeatability of those tests, about the reliability of the results that we obtain. Except that in the case of fatigue testing, to get even 1 point takes a long time. If we are testing at 1.5 hertz or 1 hertz and the test goes on for a million cycles, I would leave it to you to determine or estimate how much time has been spent when that beam and all that experimental apparatus has been occupied applying the load on the member. And in order to carry out 7 or 8 tests to better understand the different materials that are being used, their efficiency and so on, it is a very, very time consuming exercise. It takes not only time, but all kinds of other resources. That is why it is important to understand the material behavior, the interface behavior in terms of numerical models supported by experimental results, so that the basic design can be carried out based on the analytical results with only a few points on the periphery or benchmarks being established using experimental results. Before we close the discussion today, I would like to acknowledge the material used from the Japan Society of Civil Engineers publications and the permissions from my advisor and guru, Professor Umoto, and also thank some of the students who have been part of my classes, who have put together some of the material here. And as is usual, before we finally close the discussion, let us take some things back home, list some of the repair materials and their properties, how the properties affect the interfaces, study the details of the methods of repair discussed, the materials, the procedure, quality control, whether it is fiber wrap, whether it is MS plate bonding, whether it is RC jacketing and so on. You could make a list of 10 case studies of major repair and or reinforcement work which are reported in literature for different bridges, for different buildings, and examine the details. There are case studies where crack injection and repair has been carried out on large dams. We could get information about the design guidelines available for repair and rehabilitation work. And lastly, mention was made of a parameter called A by D in the context of testing of beams, which were being tested for repeated loading. What's the importance of this parameter? If you would remember, the value that was used in the present study for A by D is given as 5.1. Now, what's the importance of A by D and why one should use numbers greater than 5 when we are testing reinforced concrete beams is something which you can think about. Thank you.